Hello everyone, I am Zach Peterson. Welcome back to my channel, and as you can tell, I'm in a new filming space, and I'm very happy to be talking to you today all about PCB design. And specifically, we're going to be looking at a topic that's very important in high-speed design, which is return paths for differential via transitions. Now, I've talked about via impedance and via design and differential vias and those types of topics in several instances on the Altium Academy channel and in a couple of videos on this channel. But today we're going to be looking at a viewer question that asks me to compare some specific differential via transition designs, including the placement of the stitching vias. So that's what we're going to be looking at today in this video. Let's hop in and get started. So in this video, we're going to be talking about some via designs and specifically how to design the return path for vias using stitching vias. So this is something, again, I've addressed in some detail in another video, but I want to look specifically at this question because it deals with some common stitching via arrangements on differential vias. So let's take a look at this viewer question. This question comes from Julia Flipson, and here you can see that she is referencing an article on my company website, and she is asking, I was wondering if you have expounded on the following topics, as I cannot seem to find much information about it online in a nice teaching way, and currently my company does not have a simulation tool. Well, that's why you contact me, because I do have access to some of those tools, not all of them, but I'm very happy to discuss this in a video. So here we have two topics that we're going to look at in this video. And so the first topic that Julia brings up is Antipad design. Now again, I have talked about this a little bit in another video on my channel, as well as another video on the Altium Academy channel, and I will link to that related video in the video description. So check out the description to get a link to that video, as well as some other resources that discuss this topic of Antipad design. The next is return via placement in relation to the direction of trace entry to the signal via with single-ended versus differential. So again, I've discussed this in a little bit of detail previously, but what I haven't discussed is these very specific options that you can see right here. Now you can see here with these options, we have three options here with the placement of stitching vias in relation to the traces of a differential pair. Now, these three options, options 1, 2, and 3, are something that I see pretty commonly used. And then there's a fourth option right here, which is where you basically take option 1 and option 2 and combine them, and then you have 4 stitching vias totally surrounding the differential vias, as you can see right here. So, such as these 4 examples below. Her current understanding is that option 4 is always ideal, unless you do some custom transition design or simulation, but it takes up the most space. So it is true, it does take up extra space because of course you have to have room for these additional vias. However, it's very difficult to say that option 4 is just always better than options 1 through 3. It really depends on what you're trying to do, and in particular, what is the channel bandwidth that you need to accommodate in this via transition. So what we're going to do now is hop into Symbior, and we're going to look at some via transitions. And first, what I want to do is address the case of the single-ended via. So here you can see inside of Symbior, I have a single-ended via with one stitching via that I've created. And we're going to do a little bit of analysis on this via to see what we can learn about how the stitching via impacts signal propagation. Now here I've created a stack-up that would be pretty common of something that you would see with a 6-layer stack-up. We have a thick central dielectric, we have 2 thinner outer dielectrics, and I've shown some examples of this in some projects on the Altium Academy channel. So again, pretty common format for a 6-layer stack-up. For the materials, we have a DK5 dielectric, with a loss tangent of 0.008 at 10 gigahertz. This would be like an advanced FR4 or maybe a less advanced PTFE. Could cover a range of different laminates, but you get the idea here. This is basically a DK 3.5 laminate. So not super low DK, not necessarily a standard FR4 laminate. You get the idea. So next, what we want to look at is the case of Antipad design. And I think it's easiest to see the role of the Antipad design by looking at a single-ended via. And then once you understand what the Antipad does conceptually, you can apply that to a differential via. So here you can see in the pad stack, I have an option to set the Antipad diameter. I can also set an Antipad diameter for my stitching via. Now here, we're basically doing what we could be considered a class 3 via. So here we have a 10 mil drill diameter for our signal via as well as our stitching via. So you can see here we have a 10 mil drill, and then we have pad size of 22 mil. So at the highest IPC producibility level to hit class 3, you would have a 20 mil pad. Here we have a couple mils over, this would be a 22 mil pad. So one thing we need to do here is we do need to set an antipad size for our stitching via, and then it is of course going to bypass some of these planes. So here we're going to have it bypass signal layer 3. So this would be like having signal, ground, power, signal, ground, signal. So again, pretty common for a 6-layer stack up. And you can see here the antipad appears right here. So we basically have 4 mils of clearance between our pad on these bypassed layers and the antipad in the plane layers where this via is passing through. And then we have the same thing on the stitching via. So now let's see what happens if we take our signal via and we change the size of this antipad, and we can see what happens to the impedance. So if I make the antipad really large, you can see here what happens to the impedance. You can see here that the impedance looks inductive. And this is one of the things that I was referencing in that older article that Julia referenced on my company website. You can see here very clearly that the via impedance appears very inductive, reaches a very high value at multiple gigahertz frequencies, and then it starts to look capacitive again, and then it starts to drop off. Now, if we make this via antipad really small, like let's say 25 mil, you can see here that the capacitance of the antipad takes over. And instead of looking inductive at lower frequencies, it actually looks capacitive at lower frequencies and then starts to look inductive again. Now, of course, if you compare here this 25 mil or 28 mil or whatever diameter to this 22 mil diameter, you'll see here in this case I've changed it to 28 mils, but that basically leaves 3 mils of clearance between a pad on layer 2 and layer 5, or layer 3, and the nearby copper. So that's a pretty small clearance. And so if we set this back to 30 mil, you can see that this is pretty optimal. Now, what about the location of the stitching via? What happens if we change the location of that stitching via? Well, let's go ahead and change this just as an example. Instead of being 40 mil away, we make it 80 mil away. Well, there's something that really important that happened here. When we made this stitching via 80 mil away from our signal via, you see that this green line moved to the left. So previously it was between 10 and 15 gigahertz, about 12 gigahertz, let's say. And then here in this case, when we change this to an 80 mil distance, you can see it's just above 5 gigahertz, so basically 6 gigahertz. So this green line is the localization frequency, and it basically tells you how good of a return path you have in this via structure. So this localization frequency is very important because it basically tells you at what frequency this via transition and its stitching via starts to radiate. It also tells you the frequency at which you start to get really strong EMI or crosstalk susceptibility into this via structure. So you have to remember that radiation is actually reciprocal. If you radiate strongly at one frequency, you can also receive radiation very strongly at that same frequency. And that's basically what this green line is telling you in this graph. So it's not just the antipad size that matters, it's also the stitching via location that matters, particularly for defining the return path. And we have a much tighter or stronger return path when we have a much higher localization frequency. Now, I'd like to point out the frequency ranges that we're talking about here. Here we're talking about multiple gigahertz frequencies. So listen, if you're dealing with just SPI interfaces and that's the fastest thing on your design, just put a stitching via somewhere. You don't have to like intentionally design every antipad and very intentionally design every single stitching via location. Just put a stitching via somewhere and you're going to be fine, right? This distance of 40 mil or 50 mil or whatever, you've got really good localization up to 10 gigahertz. That's going to be just fine for a SPI interface, especially if it's on a 6-layer board like this where you've got a lot of copper in multiple plane layers. But if you're dealing with something that requires, let's say, much higher channel bandwidth, maybe it's multi-gigabit per second Ethernet, maybe it's PCIe, maybe it's DDR4 or 5, something like that, then you absolutely do need to design these antipads very carefully and make sure that you have the required impedance and localization out at least to the edge of the channel bandwidth requirement. And then you need to look at the S parameters for that via transition to ensure that this via transition doesn't create excessive return loss. So now let's take a look at some of these arrangements where we have differential pairs with stitching vias. So here I have a differential via that I've created in Symbior, and you can see here that we have an impedance spectrum for it, and you can see here that we have our localization line. So this localization frequency, again, an indicator of how good of a return path you have created in this via structure. So let's take a look at how some of the parameters impact this via transition. So here we have two stitching vias, okay? And these are located at a distance of 50 mil away from the signal vias. Now, these vias have pretty tight coupling at 10 mil distance, so just a little above 1 W. And then here you can see that we're basically targeting 100 ohms. Now, here you see that this is 98.81 ohms. It's a little bit low just to account for copper roughness. And of course, I've done another video about roughness compensation in or on the Altium Academy channel. You can find a link to that video in the description. But for now, let's take a look at what happens with these stitching vias. Okay, so first, what's the role of having two stitching vias? How do we determine that? Well, to understand that, let's compare this with the case of one stitching via. So if we have one stitching via, what happens? Well, here you can see that the localization frequency basically moved from about 47 gigahertz down to what looks like 28 or 29 gigahertz. Basically got cut in half. Okay, so we can clearly see that the stitching vias do have a role in determining the return path, but they don't really have a role in determining the impedance in this differential via transition. And if you watch the other video that I referenced about stitching vias and differential via transitions, then you'll know that the differential via transitions are primarily dominated in their impedance by the antipad when the antipad is much closer than the stitching vias. There's also the via to via distance that helps determine what is the impedance of this transition. So the main role of these vias is to help determine the localization frequency and to help determine the frequency at which the return path is confined in this via structure. Now, just for fun, let's compare this with the case of 0 stitching vias. What happens to the localization frequency? Well, here, having no stitching vias is basically the same as having only one stitching via. You can see here, again, the impedance is basically unaffected according to the via analyzer model, and the localization frequency has basically moved back to the same frequency of about 28 or 29 gigahertz. So here, this very tight antipad that we have of basically 30 mils is pretty much dominating both the impedance and the localization frequency when we have only one stitching via or when we have no stitching vias at all. Now, again, the other factor that helps determine this localization frequency is not just the location to the edge of the antipad, it's also the distance between these two vias. So these two vias being tightly coupled like this distance is also a major determinant of the localization frequency. So which one of these two factors dominates? Well, you kind of have to run through these different parameters to really determine that. And it's a bit difficult to generalize, and I would love to give you kind of a general rule of thumb about what you should do here, but the problem is that these structures are so complex, especially once you start to get to higher and higher layer counts, and you have stubs like you have here. It's very difficult to generalize what is the best way to design these antipads and these distances between the vias in order to hit your impedance target and have these really high localization frequencies. In general, if you make this differential via center-to-center distance smaller and you make this antipad smaller, you can overcome the inductive effect that I showed earlier with the single via, where you had the inductive slope early at low frequencies, and then it starts to look capacitive at higher frequencies. And that's exactly what we see here in this differential via. But here, with this center-to-center distance being so small, it also impacts what is the localization frequency. And we can test that just by making the antipad on this differential via transition very large. Let's suppose, just as an example, we make it 60 mil. You can see here that the impedance spectrum changed, but the localization frequency didn't change. So because the localization frequency basically remained the same, we can say quite clearly that the localization frequency in this via transition is basically dominated by the via to via distance rather than the via to antipad distance. So now let's look at the case of whether the stitching vias are located here, located above, or located along the same line. So here you can see I've reset the stitching via locations, and you can see here that we have the trace entry coming from the top up here on the top layer. Now, what if we just changed it to come between these two stitching vias? Well, we can do that here on the Inputs tab, and if I just click this, you can see that it changes the input trace direction to come between these two stitching vias. And you can see it's basically no effect because, again, the stitching vias are helping to determine the localization frequency, but you also have the tight coupling here that also helps determine the localization frequency. Now, I've talked about whether or not you need tight coupling for differential pairs to function, again, in other videos. It is not a requirement for it to function. If you had loose coupling, meaning you basically just had a larger distance between the vias in this differential via transition, then it's certainly possible to compensate for that by putting, for example, the stitching vias closer. So there are a number of different ways you can still hit your impedance target without requiring that the two vias be very close together. Now let's take a look at this. What if we just swap, again, the location or the distance of the output traces here on layer 4. You can see, again, the impedance and the localization frequency are basically unaffected. So it kind of doesn't matter what area or what direction we enter from. We can still basically have a via transition that's unaffected due to the tight coupling between the differential vias. Now, what about the case of 4 stitching vias? Are they always better than the case of 2 stitching vias? Well, here you can see I've set up 4 stitching vias in this model, and as you can see, the impedance curve is still basically the same, the localization frequency is still basically the same. So again, 4 stitching vias not automatically better than 2 stitching vias. Now, again, part of the reason for this is because we have this tight coupling between these vias in this Stackup. So these 2 vias, again, separated by a clearance, pad-to-pad clearance of 10.5 mils, and that really dominates setting the localization frequency and the impedance in this differential via transition. So in everything we've looked at so far, what we've found is that when you have a case of tight coupling between the differential vias, you can reach a state where the number of stitching vias doesn't really affect anything in this transition. You need to have a couple of stitching vias in order to have a localization frequency and good return path all the way up to, as you can see here, in the 47 or 48 gigahertz range. but it is not required to have a large number of stitching vias, like 4 stitching vias, as you can see here. And as we can see, this is all dependent on the spacing between the differential signal vias. Now, what if we changed this to, for example, 50 mils instead of 30 mils? Well, you can see here when I change this to 50 mils, you can see here that the entire impedance spectrum changes. And now we've seen that the localization frequency decreases. That's because we basically made a larger resonant cavity between these two vias in this via transition. You can also see that the impedance spectrum changed. So now the impedance spectrum has increased in this frequency range up to the localization frequency. And you can see here that if you were targeting a 100 ohm impedance for this via transition, you can see that in this case, you've really only achieved that up to about a couple of gigahertz. So making these vias very far apart has the possibility of totally ruining that via transition in terms of its impedance. Now, what if we also compensated for this by, let's say, increasing the spacing between the traces coming in to these vias? Let's say we were to maybe make these 20 mils and maybe also make these 20 mils, and then we compensate for our transmission line by making these just a little bit wider. You can see here that we can still get a good impedance match coming into these vias, but again, the via impedance spectrum is basically unaffected. What we would need to do is then change the size of the antipad in order to overcome this inductive effect here, as you can see in these mid-range frequencies. So for example, if I made this antipad just a little bit smaller, you can see here we overcome that inductance just a little bit on this rising edge of these impedance curves. But unfortunately, in this particular stack up, you can see that if I make my plane layer antipads 25 mils in order to add some capacitance to overcome this rising slope on this impedance curve, how much clearance does that leave us between this pad edge and the antipad edge? Well, it only leaves 1.5 mil. So that's basically going to be unacceptable for PCB fabrication. So if we wanted to continue to improve this via transition, unfortunately, the only option is going to be to change the stack up. This is one of the reasons it is so hard to generalize via transitions at multi-gigahertz bandwidths. It is because it also depends heavily on the PCB stackup, the materials involved, how many layers you're passing through, whether or not you're using, for example, through-hole or blind and buried vias. It depends on so many factors that it's just very difficult to generalize. While I wish I could give you a rule of thumb that covers via design up to multi-gigahertz channel bandwidths for every stackup, it just isn't possible. You really do need access to a simulator like Symbior or something like Polar Instruments to help you design these via transitions. So make sure to consider that next time you're looking for a simulation tool or an impedance model for vias that is valid out to many gigahertz channel bandwidths. Thank you very much for the question, Julia. And of course, if you are out there watching these videos and you have a question about PCB design, you can get a hold of me on LinkedIn and send me your questions. And of course, if you ask a great question, it just might end up in one of these videos. Make sure to hit the subscribe button, hit the like button, and I'll see you all next time, everybody.